session number 26 in the series Analog Circuit Design using ADS. I'm Anurag Nigam, and I'm going to take you through mixer design in this session. Now, mixers have a lot of applications. The most important application of a mixer is going to be in a communication system where you upscale the frequency from baseband to a carrier frequency. So let's look at a particular mixer which is called a Gilbert cell mixer. Gilbert cell mixer. Okay, so now what is the basic unit of a Gilbert cell mixer is something called a translinear cell. So let me just write it down. It's a translinear cell. Okay, so what's a translinear cell? A translinear cell is nothing but two transistors which are connected like a differential pair, right? And then you are pulling certain current out of it called I tail. Now what happens is when now these are given two inputs, let's say V1 and V2. Now when V1 is equal to V2, right, then the two currents ID1 and ID2, they are going to be equal. So ID1 is equal to ID2 equal to ID, right? So this is what happens. Now if I apply a certain differential voltage V1 minus V2, then one current would go up. So for example, V1 is higher, right? So this is a positive quantity, right? So V1 is higher than V2, right? So in that case, ID1 will go up and ID2 will go down, but the sum ID1 plus ID2 will be equal to I tail. So that's what happens, right? Because this current basically is divided into half when V1 equal to V2. But now if V1 is greater than V2, then this happens. If V2 is greater than V1, then what will happen is ID1 will go down and ID2 will go up. Now let us write down the equations for ID1 and ID2. Now these ID1 and ID2, they are going to be large signal variations. So we would write a large signal equation for this. So ID1 is going to be equal to mu n cox by 2 w by l. So let's say each one has a size of w by l, right, into square root of I tail. So remember, I tail basically when V1 equal to V2, then I tail ID1 is equal to ID2 equal to ID, which is equal to I tail by 2, correct? So now I tail by, so this is going to be twice of this quantity. So let's represent this quantity as K. So let's go ahead and represent this quantity as K. Just one second. Okay, so this quantity is K, right? So what is K? K is equal to mu n cox by 2 w by l. So this is K. K times, so basically this will be equal to minus Vi by 2 whole square. So this is the large signal current ID1, right? Similarly, we have ID2. ID2 will be equal to K times of root of I tail by twice of K, or small or big K, don't get confused. Okay, so let's correct this. Twice of K minus V1, right? So this is 1 and this is going to be V2, isn't it? Just one second. Okay, the issue here is, let me write this again. we are dealing with differential input as vi1 minus v2, right? So now this is vd and this is vd, correct? Now we have here vd square by 4 minus, so this is a plus in one case, this is minus in one case, vd by 2 square. Now let's verify this. If vd is equal to 0, then id1 would be equal to k times of, so vd is 0, right? So square root of I tail by twice of k, right, plus vd is 0, right? So under a case vd equal to 0, this is square, right? So this will be the first term when vd equal to 0. So that would be k times of root of k, right? Okay, so this term is equal to twice of id by k, right? So this is going to be twice of id by k mu and cux by 2. Okay, so this will be v overdrive by 2 square. So it will be v overdrive by 2 times of a square, which will be k times of v overdrive square by 2, right? Okay, so let me check this. Twice of id, 2 will cancel out, I tail by 2, hang on. Okay, so we don't have to do that complex maths here. Okay, so we just have this term, and this term would equal to, if you just do the square, right? So this will be I tail by twice of k and k. So this will be I tail by 2, right? So id1 is equal to I tail by 2. Same is the story for id2, which will be I tail by 2. So when the net voltage, differential voltage equal to 0, then this is the situation, that id1 is I tail by 2 and id2 is I tail by 2, right? Now when certain voltage is applied, then we will have id1 differing, so it will be k times of, so it will be differing, it will be k times of square root of I tail, because it is a last signal variation vd, right? So it will be twice of k minus vd square by 2 minus vd, so plus vd by 2 whole square, right? So this is the case. Okay, so this is by 4, sorry, by 4. Okay, and id2 with the vd applied, differential voltage vd applied, will be I tail by 2 of k minus vd square by 4 minus vd by 2 whole square. Is that right? Okay, now the total output current is the differential current, id equal to id1 minus id2. So when you do that, you are left with k times of a plus b square minus of a minus b square. Okay, so this will be a plus b, so a plus b will be, a plus b would be a plus b into a minus b, a minus b. Okay, so this will be the term. So in that case, this would become, right, so in that case this would become 4 times of A into B, correct? So in this case, A is equal to square root of I tail by twice of k minus Vd square by 4, and B is equal to Vd by 2. Am I right? So then the answer is going to be ID will be equal to 4 times of, okay, so there will be a k term, 4 times of k times of I tail by twice of k minus Vd square by 4 times of Vd by 2. So that will leave 2 here. So the differential current ID equal to ID1 minus ID2, which will be equal to twice of k times of root of I tail by twice of k minus Vd square by 4 times of Vd. Okay, so this is the situation. Now if I was to plot this, right, so if I was to plot this currents, right, so let's see what will happen. Okay, so this one represents a Vd of 0. This represents a Vd of 0. So at Vd, sorry, this represents Vd equal to 0. So at this point, both the currents are going to be ID, which is I tail by 2. Correct? Now, if I assume a point here which is minus root 2 times of V over drive, and over here I assume plus root 2 times of V over drive. So let's find out its value. Okay, so just one second. So at this point I want to plot the currents ID1 and ID2, right? So if I substitute minus root 2 times of V over drive in ID1, right? So in ID1 minus root 2 times of V over drive. So let's take the ID1 here. So ID1 at minus root 2 times of V over drive. Okay, so this would be equal to k times of k times of I tail by twice of k, root of I tail by twice of k minus Vd square by 4, right? So Vd is going to be 2 V over drive square. So it will be 2 V over drive square, right, divided by 4. Okay, minus of root 2 times of V over drive by 2, the whole square. Okay, so now V over drive can be written as k times of V over drive. Let's write that. So the current is equal to ID equal to, let's say, I tail by 2, right? Okay, in terms of V over drive, it is k times of V over drive square, right? So then I tail by twice of k is equal to V over drive square, right? Now in this case I have to substitute V over drive, right? So V over drive square, right? Okay, so V over drive square. Okay, so then V over drive basically square root of I tail by twice of k, correct? So let's substitute that over there. So we would have k times of square root of I tail by twice of k minus v overdrive square I tail by twice of k, right, times of 2. So this will be 4 minus of root 2. So it will be root of I tail by twice of k and square root 2 divided by square root 2, right? So 2 will come inside, right? 2 will come inside as 4k square. So now this leaves me as root of I tail by 4k minus root of I tail by 4k. This terms cancels out, whole square k times. So id1 will be equal to 0. So if at this point id1 should be 0, right? So here id1 equal to 0. What about id2? Okay, id2 at this point at minus root 2 times of v over I. So let's substitute it. Okay, so in this case there will be a plus sign over here, right? So then id2 would be equal to k times of square root of I tail by 4k times of 2 whole square, isn't it? So in that case this 4 will come out and this 2 will cancel. It will become root of I tail by k square. So that will be equal to I tail. Okay, so at this point id2 is equal to I tail, right? And same thing will reverse here. Here id1 will become I tail and id2 will become 0. Okay, so the curve goes like this. So if I was to draw id2, right, so this is id2 and it will cross over here and like this, and id1 would go like this and it'll cross over here and go like this. So I can draw it like that and I can draw it like this. Okay, and this value is I tail. Sorry. Okay, so this is how a translinear cell works. Now the input voltage range where you see the gain is from minus root 2 times of v overdrive to plus root 2 times of v overdrive, where we are going to see this gain, correct? So if you increase the gain, then root 2 times of v overdrive to plus root 2 times of v overdrive, this is going to shrink. So basically if you want a higher conversion gain, okay, then you are going to lose the input voltage range. So this is what the translinear cell says. Okay, so just keep in mind this response of a translinear cell, and also keep in mind this thing, which is id, the difference of current is equal to this thing. Okay, now let's go to a Gilbert cell mixer design. So what is there in a Gilbert cell mixer? In a Gilbert cell mixer you have a RD and you have a RD. So let's say the current here is going to be I7 and I8. So this current is I7 and let's say this current is I8, correct? Now here I am going to have one translinear cell. So this is one translinear cell over here. So this is one translinear cell, and then I'm going to have another translinear cell over here. Correct? So I have two translinear cells. and this output, this is basically connected over here, and this is connected over here. Okay, so if I assume that the currents in this translinear cell are ID 3, 4 and 5, 6, so this is ID I3 and this is I4, correct, and then this is I5 and then this is I6. So I can write this, okay, I7 is equal to I3 plus I5, and then I can say I8 is equal to I6 plus I4, right? Then the difference of the two currents, right? So difference of the two currents would be I7 minus I8 would be the output difference, which is basically I can write as I3 minus, right? So I can say I3 plus I5 minus of I6 plus I4, right? So I can always write this as I3 minus I4, right, and minus of I5 minus I6, I6 minus I5, right? Okay, so the inner currents are subtracted from the outer currents. So basically outer currents are I3 and I6, inner currents are I4 and I5. So I have I3 minus I4, I6 minus I5, and then the subtraction of that, correct? Now, okay, now the whole circuit is like this. I have got RD, and here I have got RD again, and here I have got a translinear cell like this, and here I have another translinear cell like this, right? So this is another translinear cell, and this is cross connected over here, and this is cross connected over here, and then I have this also as a input here, here this is connected like this, right? And then there is a I tail here. Okay, so there are one translinear cell, two translinear cell, three translinear cell. This is I1, this is I2. So basically I tail equal to I1 plus I2, and then here this current is I7, this current is I8, then this current is I3, and this current is I4, and this current is I5, and then this current is I6. Okay, so this is the complete picture, and the inputs go like this, that this is connected, so let's do this connection, is connected here. So this is one terminal and the other terminal is over here. So let's say this voltage is plus minus Vy, right? And then you have got this voltage, okay, plus minus Vx. Okay, so in this scenario we want to find out what's going to happen. Okay, so we were at this equation, right? So we have I7 minus I8 equal to I3 minus I5, right? I3 plus I3 minus I4, so I3 minus I4 minus of I6 minus I5, correct? Now I can use a equation which is basically over here, ID1 minus ID2, right? That ID1 minus ID2 is over here, right? So here it will be twice of K, and this VD will be, in one case it will be okay, so I'm going to use K common. So K is basically your mu n CoX by 2 W by L. So let's assume that all these transistors are same size. This one, and this. All these translator cells, so they have the same K up, top and bottom. Right, so in that case, this would be equal to twice of K times root of I tail. In this case, I tail will be I1 by twice of K minus V overdrive square by 4. In this case, not V overdrive, sorry. It will be Vy. Okay, so I'm writing for the top one. Vy is the input, right? Vy square by 4, right? Times of Vy, right? Okay, and then the other term would be minus of twice of K root of, okay, so this will be bracket, right? So root of I1 by twice of K minus, okay, so in this case it will be I2, isn't it? It will be I2. Okay, so one current is I1, other current is I2. I2 is Vy square by 4 into Vy, isn't it? So into Vy. So I'll take this Vy common, twice of K Vy, and then I'll be left with I1 by twice of K minus Vy square by 4 minus root of I2 by twice of K minus Vy square by 4. Okay, so this is going to be your output current ID. Now here I1 itself is going to be twice of K times of root of, okay, I tail by, oh, sorry, just 1 second. I1 will be equal to K times of by twice of K minus the differential input, right? In this case it will be Vx square by 4 plus Vx by 2 square, isn't it? And I2 will be equal to K times of root of I tail by twice of K minus Vx square by 4 minus Vx by 2. Correct? So now I'm going to substitute this in that, and if for a condition that I tail by twice of K minus Vx square by 2 plus, okay, okay, plus Vx by 2 for this condition greater than, so this is going to be much greater than Vy by 2. So in that case what is going to happen is, in terms of this, it will simplify to I tail is equal to 4 times of K times of Vx times of Vi. Okay, so you can do the maths. So this would be your output current. Okay, and then the output voltage VO will be equal to ID times of RD, which will be equal to 4K times of RD times of Vx times of Vy. Now notice this one is the conversion gain, GC, Vx Vy. So VO, so if I consider one of them to be, so this is not GC, just 1 second. So if I consider Vd by Vx, okay, so one of them has to be absorbed in, so 4k, so I can absorb here Vy, right? So it doesn't matter. So this I am going to absorb here Vy and Vx. So this then Vo by Vx basically is equal to 4k Rd times of Vy. Okay, and this quantity is known as the conversion gain. Okay, so if you give a x input, right, then the output is going to be proportional to the multiplication of x with y with the conversion gain, right? So if you can see this term here, this shows that the two signals get multiplied. Vx is controlling the GM of the top. So how the mixer works, Vx controls the GM of these guys. Okay, so Vx controls the GM of these guys. So basically GM is a function of Vx. Next is the output Vo is minus GM RO, right? So in this case it will be the GM is a function of Vx, okay, and then times of gain, right? So it will be Vy. So GM RO is the gain, right? So in this case the two signals are getting multiplied, right? So the simple way of understanding this is I am making a multiplier. The bottom signal Vx is controlling the GM of the top transistors, and so that's how Vx comes into picture. And then the Vi is being amplified by this top transistors with gain, which is a function of GM times of RO. So that's why the two signals Vx and Vy are going to multiply. Okay, so this is how a Gilbert cell works. Now if k is the top one have k1 and k2, so if the two transistors differ in size, then this equation Vo will become 4 times the root of k1 k2. So this is a geometric mean, right? K1 k2 times of Vx Vy. So this is a condition when the top and bottom Gilbert cells are not same, and if they are same, then it will be 4 times of k times of Vx Vy. So this is how the signal is multiplied. Now if the signal, okay, is cos A into cos B is going to be equal to cos of A plus B by 2 plus, so I might be wrong in trigonometry, but what it will give you is the sum and difference signals. So you see sum and difference signals, right? So if there are two frequencies, let's say omega 1, so cos of omega 1 t, and then you have cos of omega 2 t, then one of them will give you omega 1 plus omega 2, and the other one will give you omega 1 minus omega 2. So basically you can either up convert or you can down convert. So that's how the mixer is used, right? So it is based on multiplication. Okay, so enough of talks, let's go ahead and design this. Okay, so to design a mixer, you go here and make a new schematic, and I'm going to call this as Gilbert 1. Gilbert 1. Create. Right? Why it's not responding? Okay, so that's Gilbert 1. Okay, so I'm going to take only NMOS transistors, right? So very quickly I'm going to put here NMOS devices. Okay, so I want NMOS devices. So where do I find them? I find them over common gate here. Okay, so let's pick up this device. Edit copy. And I'm going to say edit paste. That's that device. And let's size them. Okay, so 130, 1.52. Okay, so all are 130, 1.52. So I'm going to make 130 nano and 1.5 into 2. So why is it so slow? 1.5 into 2. Okay, so now in this case K1 equal to K2. So I'm going to repeat this one. So this is going to be my one translinear cell. Correct? So this is one translinear cell. I'm going to repeat it. Okay, so rather let me just connect it first. So this is connected over here. This is connected over here. Sorry. Okay. Fine. So this is one translinear cell. Correct? And then I have another translinear cell which would be connected over here like this. Right? And then I have a third translinear cell which would be at the bottom. So this is the third translinear cell which is at the bottom. Correct. Okay, and then I have got this as Vy and this as Vx. So this is going to be your Vy, and this is connected to this one. Sorry. So don't worry about this. That's the connection. So now we have these connected Vy, and then we have got Vx. So this is your Vx. Okay, and then I have to put a I tail, right? So in this case I will put a big transistor here, right? So I will take one of the transistor and I'll make a current mirror over here. So over here I'm going to make a current mirror. This is going to be 2.52 and this is going to be 20. So this is a 1:10, or let's say 1:8 current mirror. So I'm going to just repeat it, flip it, so it goes over here. Correct? And F5 goes over here. Okay, let me see if I'm recording. So I'm recording, fine. So the next thing I'm going to do here, next thing I'm going to do is the diode connection, the body connection here to its source, and this is a diode connected transistor, right? And this is pulling out the tail current from here, right? So we are all set with the design, only we have to put resistive load here. So I'm going to put 2.5k. So go to lump components and I'm going to put here 2.5k over here and 2.5k over here. Later I can change them if I want, right? So where is it stuck? And why is it stuck? Okay, So this is 2.5k. So this is RD. So this will decide the conversion gain, right? 2.5k. Okay. So this is connected over here, and this is connected over here. This is connected over here, and this is connected over here. Correct? So we are all set now. This is going to be our VDD. Like this. So let's put the pins, right? And the pins are going to be, this is VDD, this one is ground, so there is a ground pin over here, right? So this is connected to the ground, correct? And then this is VXP and VXM. So this one is VYP, and then we have VYM. Okay, and then we have VYP, VYM, then we have VXP and VXM, and VXP. Correct? And then you have got VOP. This is VOP. And this is going to be VOM. Correct? And one more quantity is going to be there. Okay. The other quantity is going to be IREF here. So this will be IREF. So this will be biasing the tail current. This will be providing the tail current. So this is a current mirror for the tail current. So now we are done with the Gilbert cell mixer. Now you can design it elaborately because you know what is the conversion gain. So you can design for a given conversion gain. But another thing is that the conversion gain trades off with the input voltage range. The input voltage range is basically going to be twice of root 2 times of V overdrive. So if you take the conversion gain up, okay, by GM or mu n CX by 2W or by K, right? If you take conversion gain up by K by increasing W by L, then the overdrive is going to go down. So there is a trade-off between the gain, which is basically the slope of this, and the input voltage range overdrive. Okay, so this is the trade-off. Now if you make the transistors to be very small, right, then the input voltage range, which is linear gain, is going to be large. So this would be a multiplier. But if you make them transistors to be large, then the input voltage range would be small, and this would be a mixer. But then if you do this, the harmonic distortions are going to increase. So if you want that, your mixer should have very good harmonic response should be low, then you are supposed to use very small devices. Okay, so that's the idea. If you want to make a multiplier, the devices are small. If you want to make a mixer with high conversion gain, the devices are going to be large. Okay, and then there is a limit on RD because of that VDD. Okay, because it is going to drop certain current here. Okay, so having told that, I am ready to make a symbol for this one. Okay, so I will go ahead and say new symbol and create a symbol. Okay, so I'm not going to use this like this. Okay, so just 1 second. Okay, so remember the input is going to be lower frequency, and the output is going to be higher frequency. So the input is going to change the GM while the signal is going to be amplified. So LO is going to be amplified, RF is going to make the change. So let's make a symbol for a mixer. So that's the mixer, and I have to put here so this is kind of stupid, but let me see if I can change this, isn't it? But then this one is asymmetric, isn't it? Okay, let's see if I can get this here. No, it is asymmetric. So stupid here. Okay, let's say this is my mixer. Fine. So I have to put in VXP and VXM as the input. So VXP and VXM as the input. Come on. Right, and then VYP and VYM as the LO. So I'll just rotate these two. Correct. I'm going to put them here. Okay, later I'll adjust it, don't worry. Okay, and then you have got two outputs. Okay, so this is VO, wrong place. This is VY, VYM, VYP. So this is VYP and this is VYM. So let's rotate this. Okay, so that's over here. Okay, fine. And then you have got VOM over here, and then you have VOP over there, and then you have VDD over here, and then you have ground. So I'm going to keep ground on this side, and I'm going to keep RF on the left side, or I can keep RF at the top, right, because I have to put in a current here, right? So I will keep RF at the top here. Correct. I can throw this one out, and what I'm going to do is turn off the snap grid and adjust these. This is VYP and VYM. And this is the ground. This is IRF. Correct. And I'll make a connection. So this is basically the ground. Fine. So this is our mixer. So let's also design. So this I'm going to save. Okay. So let's say if we are going to operate this from 2.4 volts, right? Now there is going to be a certain voltage VXP, VXM. So there will be a common mode voltage here, right? That will be VGS, which will be V overdrive plus VT. So it will be twice of V overdrive plus VT will be the common mode for X signal. And then you will have V overdrive, V overdrive. So thrice of V overdrive plus VT would be the common mode for VY, right? So if you are clear with that, then we can go ahead and test this one. Okay, so LO VCM2, right? So basically that's the LO. So I'm going to put here LO on VY, and I'm going to put here RF in VX, correct? So that's fine. So we have figured out everything. So now we create a schematic to test this Gilbert cell. So we say test Gilbert. Okay, create schematic. First thing is we're going to get a Gilbert cell onto it. Okay, we forgot something. So we forgot to turn on the grid. Insert options, snap grid. Okay, now we will get the Gilbert here. And I'm going to move the text over here. Let me see if I'm recording. Yes, I am. Okay, so now I'm going to put in the LO and the LO frequency, LO power, RF frequency, RF power, right? And I want to demonstrate. So this is going to be very broadband. So let's say LO is around 2.4 gigahertz, right? And IF is around 11 megahertz, which is your Wi-Fi, right? So let's do that. So let's generate a variable here, and we call this as, so we are going to have LO frequency, LO FREQ. So I am going to have this LO FREQ as 2.4, pure number, correct? Apply. Then I'm going to have the IF FREQ, IF FREQ. This is around 11 megahertz, right? So 0.011. This is just, I'm considering I'm giving a Wi-Fi baseband input, right? So I'm gonna say add, and then you have got LO power. So I'm gonna say LO power, and this LO power I'm gonna put here as 0 dBm. So add, and then I'm going to put here RF power, which is going to be again 0 dBm because we're going to sweep it anyways, right? So I'm going to add RF power, and then I'm going to have two common mode voltages, VCM1, which is for the lower stage, which is VX, VCM1, or rather VCX, I would say VCMX. This would be around 1.2 volts, and then I am going to have VCMY. So this is going to, for the IF input, is going to be 1.7, right? Add and say okay. So we have generated all the signals. Now we are going to put in the sources and the currents. Okay, so I'm going to operate this from 2.4 volts. So we'll go to sources, frequency domain, and this is going to be 2.4 volts. 2.4. Okay, so this 2.4 is connected to VDD, and then you have a IREF which is 40 microamperes. So you can design for any IREF, right? It's just that you be careful that you do not run the headroom, so that your transistor should still be operating in saturation region, right? So here I'm going to put here 40, let's say microamperes, correct? And I'll connect it over here, and then I have got ground which is connected over here, and then I have got IF input. So I'm going to go to P1 tone, okay, and this would be IF FREQ. IF FREQ is the frequency in gigahertz, and this is IF power. IF power, correct? So this is okay. So one more mistake I have done. This has to be IF power, not RF power. I'm doing an up conversion, right? So IF power. So this is IF power minus 3. because this is a differential input, right? So another 3 dB will come from the other terminal, right? So -3 over here. Then I'm going to repeat that to generate a differential, right? So one more thing I have to make sure that here I am going to have Vx, right? So Vxm, so DC voltage is going to be equal to Vxm, and oh sorry, DC voltage is going to be equal to Vxm. Okay, so Vx is the bottom, right? So it will be less, right? Vxm is 1.2. Okay, and I'm going to display this. So that's your this thing. Then I'm going to repeat this and give a 180-degree phase shift. So that will be the Vxm. So this is Vxm, and here this is going to be 180. So that's my differential input. Another differential is input is for the LO. So I'm going to just copy these two and place them over here, right? So here instead of IF power, I'll do a LO power, and this will be LO frequency, isn't it? So this will be LO frequency. Similarly over here it will be LO power, and it will be LO frequency, and this is going to be VYM, and VCMX and VCMY, sorry. So this will be VCMY. So this is going to be VCMY, and this will be VCMY, common mode Y signal, and this is going to be VCMX, and this is going to be VCMX. So that's all set. So I'll just connect this over here and over here. Okay, now what I'm going to do is I'm going to put here label the outputs as VOP and VOM. So I'll put here as VOP, and then I'm going to put here VOM. Okay, so we are ready to test this mixer. All I need is a include file. So I'm going to put in an include file here, and what am I going to simulate? I'm going to do a harmonic balance on this, right? So I will go to simulation, harmonic balance, put in here harmonic balance, and I'm going to put in 2 tones, right? So in this case one would be so I'll be putting in LO frequency, LO FREQ, and this would be in gigahertz, and say apply, right? And then the order is 5, that's okay. Then I will say IF, and the order is 5, I'll say okay. Now this is the order of mixing. Okay, so this is the order for the signal, and this is the order of the mixing. Okay, so that's all you have to remember. Then I'm going to do a sweep. Okay, I'm going to sweep the IF power from -50 to 0, correct? So I will be sweeping IF power. Okay, and that will be going from -50 to, let's say, 0 in steps of, let's say, 1, correct? Apply that. Is that okay? Okay. So we have harmonic balance set up, we have everything set up. Now all we have to do is hit simulate, right? So if I hit simulate, okay, so we didn't get any errors, right? Okay, now we have to look at the output power, right? P out. Okay, so to do that, I am going to look at P out. Okay, just 1 second. Okay, P out is going to be dBm to watts. dBm, dB. Okay, so let's write here some equations. So in this case, I'm going to write here as P out RF, right? Okay, first of all, you should know what is the which is the output. So in this case, I will switch off the sweep. So I'm not going to sweep this one. Let's look at the mix. Let's do that at a single power level. When you hit simulate, you are going to have something called a mix table. A mix table. Okay, so we are looking at mix components. Okay, so we are basically looking at the up conversion, which is 1 and 1. So this is 1 and 1. So if you mix 2.4, sorry, so if you mix 2.4 gigahertz with 11 megahertz, you are going to get 2.411 gigahertz. So this is the up conversion, right? So this is index number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be 10. So this is the up conversion, right? Okay, so this is going to be the up conversion, and then you will have 2.4 minus 11, right? So control C, control V. Okay, so that component will be 2.389. So there is a grid issue, that's okay. So don't worry about it, I'll adjust this. Can't I grab this one? Still it is not. This is so horrible. Preferences 0.0625. Just to display the things. Come on, guy. Can't select it properly. That's so horrible stuff. So one of them is over here. That's correct. Then the other one is over here. Now this one is playing havoc. That's okay. So one is going to be F1 plus F2. The other one will be F1 minus F2. So 2.4 minus 11 is 2.389. So this is going to be index number 8. So this is index 8. Sorry. This is index 8. And then the other one is going to be index 10. So this is index 10. Okay, so why am I showing you a mix table? So that you know how the mixing is taking place, right? So that's the story here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, so I'm going to put here two equations. P out difference is going to be equal to dBm to watts, dBm, right? dBm to watts of something, and that something would be dBm of that, dBm of something. Okay, so that would be VOP minus VOM. Okay, VOP minus VOM, and we are looking at index number 8. So this is going to be your difference of the frequency, and then you are going to look at the sum. So I'm just going to copy this one, Control C, V, and now we are looking at P out S. So that would be the sum. So that will be index 10, and index 10. So we are all set with this, right? And then I'm going to say the total P out is going to be the sum of the two, correct? So the total P out will be equal to P out D plus P out S, right? So that will be the total P out, and then P out in dBm. So P out in dBm will be P out in dBm will be equal to 10 log 10 of 10 times of log 10 of P out, correct? Okay, plus 30. So we are in dBm, right? So plus 30, right? 10 log 10 of P out plus 30. So this will be P out in dBm, right? And conversion gain will be this minus the IF power. So conversion gain G and dB. So I will say GC dB, sorry, GC in dB is going to be equal to P out dBm minus IF power sorry, correct? So let's see if IF power is available. So IF power is not available here, though we are sweeping it. So what we have to do here is you have to go here and go to output, and you have to add IF power to this. So this will be output in the data set, and when you simulate this one again, we have this in black color, right? So now with this I don't need the table anymore. Now I'm going to do the sweep. Okay, so now I'm going to put back the sweep on IF power. Sweep IF power, say apply. So okay, so now I'm going to sweep the power. Okay, and then I'm going to plot conversion gain. So go to equations, conversion gain in dB. So that's your conversion gain. So that's your conversion gain is around 11, correct? Right. And if I want to look at the output power, right, I can put output power in dBm equations, output power in dBm. Okay, so it is compressing, so let's put this on the right hand side axis. So now this is fine. Okay, so if I was to find out where is this mixer compressing, so over here there's a gain of 11, and if I put here this one, so 11 has to become 10. So this is 1 dB compressed over here. So at the input, so at it output power of minus 8.9, it is compressing, right, by 1 dB. So this is going to, mixer is linear, okay, up to output of minus 8.9, right, and input power of minus 19. So at the input power of minus 19, the compressor is going to compress by 1 dB. The mixer is going to compress by 1 dB. So that's the idea. And if you want to look at the spectrum, right, okay, so what I'll do is, for this mixer, I'll write just the equation for this index. So what I'll do is, I will put here another equation, and I will say n is equal to find index of something, and that something is going to be, the series is called IF power, and the value is going to call independent of M1. Okay, so that's there, and I can display the index. So I'm looking at where your M1 is, so I'm going to look at the index. Okay, so I'm at the index of 3 here, right? So you see 4, 5, 6, 7, 8, 9, 10, 11, right? So let's see the compression. So at this point the index is 31. So here the mixer is 1 dB compressed. Okay, so I can display the output, right? So it will be VOP. That's okay. We can put here dBm, fine. Okay, so here I have to go make changes. So we are looking at VOP at an index of n. So we are looking at all the frequency points at an index of n. So this is all the frequency points at an index of n minus VOM. So I'm going to do a control C, and I will do a minus of control V, and this is VOM. Okay, so now what are we looking at in dBm? That. So my concern is the up conversion, right? So I want to look here. Others are going to be low, right? So I'm going to zoom in here. So I'm going to zoom in here. Okay, so let's look at, okay, this is too much, right? So let's scale it. Minus 80 is good enough, right? So let's look at up to minus 80. Minus 80 goes over here, isn't it? Okay, so now new, so you are looking at up conversion. So 1 will be 1 plus 1, right, the mixed component, and marker new. So this will be the sum frequency, this will be the difference frequency. Come on. Okay, one is the sum frequency, other is the difference frequency. And now what you can do is, you can see how the harmonics are changing. So you see here, So it is going to become more and more linear when you back it off. So when you back off, these components with respect to that are going to go down, right? So that is there. And also in time domain I can display this, right? So in time domain I want to display this, right? So I will just copy this one, Control C, Control V, and here instead of dBm I'm going to do a TS, isn't it? So I'm going to be in time domain, TS, and here I will remove the scaling, X, Y. Okay, so this is at a particular, so I'm going to remove the markers here. I don't need these markers. Okay, so this is at the carrier frequency is over here. So basically you have 11 megahertz and then the carrier frequency, isn't it? So if you zoom in, okay, so you are going to see the carrier frequency and you are going to see the carrier is being modulated by 11 megahertz. That's all what you're going to see here. And if you vary this, the amplitude is going to change, right? So this is how a mixer, Gilbert cell mixer up conversion is working. You can also design a Gilbert cell down conversion mixer. It's the same design, it's just that you are going to connect a RF input instead of a IF input, right? And then you'll get the difference component which you are looking at as a down conversion. So this is a session on Gilbert cell mixer. We have seen conversion gain and all that. Now if you want to reduce this, if you want to increase the conversion gain, you can go ahead and increase these resistor values. So let's say if this is 5 and this is 5. So let's see what happens to conversion gain. Simulate it. So conversion gain is 11. Notice that. Now what will happen to the conversion gain? Okay, let's see. Now the conversion gain is 16, right? So basically it scales with RD, isn't it? It scales with RD. Okay. Another thing I want to tell you is that if you want to have this compression move out, then you can go ahead and reduce the sizes of these transistors. So instead of 1.5, if I want to do 1, 1, 1 and 1. Okay, now the conversion gain will slightly go down, but the things will push out in the compression. Okay, not much difference here. Okay, but the idea you understood, right? The input, if you want to improve the compression, okay, so VXP, okay, so we have to reduce this one, not that one, sorry. Okay, let's see what happens now. Simulate. This has to move out. Yeah, so the gain is reduced, but the compression point will move out. So if it is over here 14.6, you are going to look at 13.6, which is over here. So it has slightly moved out, right? So the linearity will be decided by the sizing or the overdrive, and the gain will be decided by the GM, right, or K, right? So this is a session on mixer. So I'm going to stop here and let me see if I was recording or talking to myself. Yeah, I was recording, so I'll just stop here.